In this tutorial, we'll start by clicking on the empty project icon. Next, we'll click on Browse under the Link to Geometry file area, then locate the file tutorial 9-1.igs. Now that we have the file selected, we'll click on New Simulation. We now need to change the material by first clicking on Part 1 in the Outline window, then selecting Material in the Detail View window, followed by clicking on the Import option, and then finally selecting Aluminum Alloy. The unit should now be checked by selecting the Units menu and then making sure that millimeter is selected. In order to impose symmetry conditions, we'll first click on Model in the Outline window and then click on Coordinate Systems in the toolbar. To actually insert the symmetry boundary condition, we'll now again click on Model in the Outline window and then click on Symmetry in the toolbar. Next, we'll click on the Symmetry Region item in the toolbar and then select the bottom face of the model. In the Details View area, we'll now click on No Selection and then click Apply. We need to now change the Symmetry Normal parameter to be the y-axis in order to complete the definition of the symmetry condition. The next step is to insert a static structural analysis environment by selecting this option. On the 15 millimeter long vertical face, we'll now insert a displacement boundary condition by first selecting this face, followed by clicking on the Supports and Displacement options. In the Detail View area, we'll now key in a value of 0 for the X component, and then leave the Y and Z components set to free. The final boundary condition is defined by selecting the bottom edge and then selecting the Supports option, followed by Fixed Support. In order to impose the force on the model, we'll first select the short vertical face, followed by clicking on Loads, and then select the Force option. In the Details View area, we'll change Define By to Components, and then enter 1000 for the X component of the force. We can now click on Static Structural in the Outline window in order to display both our loads and boundary conditions. For the solution types, we'll click on Solution and then select the options Deformation and Total, and also Stress and Equivalent. Since our model is now complete, we'll now click on the Solve button. As we can see, the maximum equivalent stress is reported to be 33.6 megapascals. Since this is approximately 15% less than our manually calculated value, we'll try to improve our results by using the local mesh refinement capability of Workbench. We'll start the refinement process by first duplicating the model in the Outline window, and then under Model 2, we'll click the right mouse button on Mesh and then select Insert and Refinement. Next, we'll select the edge at the base of the fillet, and then in the Details window pane, change the refinement value to be equal to 2, followed by clicking on Apply. To view the refined mesh, we'll now click the right mouse button on Mesh in the Outline window, and then select the option Generate Mesh. We can view the mesh of both of our models in a split-screen mode by first clicking on the Viewport icon and then selecting the Horizontal Viewports option. Then we'll click inside the top viewport to activate it, followed by clicking on the Mesh item that is listed under the first model. Notice that the mesh at the base of the fillet has much smaller elements in the second model. We'll now click on the viewport icon in the toolbar and select one viewport to restore the graphics window to its previous state. In order to now calculate results for our second model, we'll make sure that Model 2 is selected in the outline window, followed by clicking on the Solve button. As we can see, the results of Model 2 show a stress of 39.1 megapascals, which is just a little more than 1% different than our hand calculation.